According to the National Electrical Code, when running conduits from a cable tray system, the conduit must be bonded to the cable tray system, providing all conduits have equipment ground conductors. This requirement is in place to ensure electrical safety and maintain a low impedance path for fault currents. The purpose of bonding is to create an electrically conductive path between different metallic parts of the electrical system. This path allows fault current to flow back to the source, tripping the overcurrent protection device, such as a circuit breaker or fuse, and energizing the circuit. The National Electrical Code, or NEC, is a set of standards and guidelines for safe electrical installations. It is updated every 3 years and is widely adopted by jurisdictions across the United States. Understanding and adhering to the NEC is crucial for electrical professionals to ensure the safety of people and property. Cable tray systems are commonly used to support and route electrical cables in commercial and industrial facilities. They provide a versatile and organized way to manage a large number of cables. Conduits, on the other hand, are used to protect individual wires or cables from physical damage and environmental factors. When conduits are run from a cable tray system, they introduce a potential point of discontinuity in the grounding path. If the conduits are not properly bonded to the cable tray, a fault current may encounter a high impedance path, which can lead to a dangerous voltage buildup. An equipment ground conductor, often referred to as an EGC, is a conductor that provides a low impedance path for fault currents. It is connected to the grounding electrode system at the service entrance and runs along with the circuit conductors to all equipment and devices. The EGC is designed to carry fault current back to the source, allowing the overcurrent protection device to trip quickly and safely. When conduits contain equipment ground conductors, it might seem redundant to bond the conduits to the cable tray. However, the NEC requires bonding to ensure that the grounding path is as reliable and effective as possible. There are several reasons why bonding is required even when EGC are present. Firstly, the EGC within the conduit may not be sufficient to handle the full fault current. The size of the EGC is typically based on the size of the circuit conductors, and it may not be adequate for a large fault current. Bonding the conduit to the cable tray provides an additional path for fault current, reducing the impedance of the grounding path. Secondly, the EGC within the conduit may become damaged or disconnected over time. If this happens, the conduit will no longer be effectively grounded. Bonding the conduit to the cable tray provides a redundant grounding path, ensuring that the system remains grounded even if the EGC fails. Thirdly, bonding helps to minimize electromagnetic interference, or EMI. EMI can disrupt the operation of sensitive electronic equipment. Bonding the conduit to the cable tray creates a continuous conductive path, which helps to shield the cables from EMI. The specific requirements for bonding conduits to cable trays are outlined in the NEC. The NEC specifies the methods for bonding, the size of the bonding conductors, and the locations where bonding is required. Firstly, the bonding connection must be made using approved methods. This means that the connection must be mechanically strong and electrically conductive. Common methods for bonding include using bonding jumpers, bonding bushings, and grounding clamps. Secondly, the size of the bonding conductor must be adequate to carry the available fault current. The NEC provides tables that specify the minimum size of the bonding conductor based on the size of the circuit conductors. Thirdly, bonding is required at all points where the conduit enters or exits the cable tray. This ensures that the entire conduit system is effectively bonded. In addition to the general requirements for bonding, there are also specific requirements for different types of cable tray systems. For example, ladder cable tray systems must be bonded at each splice and at intervals not exceeding 10 feet. Solid bottom cable tray systems must be bonded at each end and at intervals not exceeding 50 feet. It is important to consult the NEC for the specific requirements for the type of cable tray system being used. When installing conduits from a cable tray system, it is crucial to follow the NEC requirements for bonding. Failure to do so can create a dangerous electrical hazard. Improper bonding can lead to voltage buildup, electrical shock, and fire. Electrical inspectors will typically check for proper bonding during inspections. If the bonding is not done correctly, the installation will fail inspection and will need to be corrected. The cost of correcting improper bonding can be significant, especially if the installation is already complete. In addition to the NEC requirements, there may also be local codes or regulations that apply to bonding. It is important to check with the local authorities to ensure that the installation complies with all applicable codes. Bonding is a critical aspect of electrical safety. It is essential to understand the NEC requirements for bonding and to follow them carefully. By properly bonding conduits to cable tray systems, you can help to ensure the safety of people and property. In summary, the NEC requires that conduits running from a cable tray system must be bonded to the cable tray system, even if the conduits have equipment ground conductors. This requirement is in place to ensure electrical safety and maintain a low impedance path for fault currents. The bonding connection must be made using approved methods. The size of the bonding conductor must be adequate to carry the available fault current, and bonding is required at all points where the conduit enters or exits the cable tray. Failure to comply with these requirements can create a dangerous electrical hazard. The purpose of the equipment grounding conductor, or EG, is to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of overcurrent protective devices, such as circuit breakers or fuses, to quickly clear the fault and minimize the risk of electrical shock or fire. The EGC is typically a wire or conductor that is run alongside the circuit conductors within a cable or conduit. It is connected to the grounding electrode system at the service entrance and extends to all electrical equipment and devices. When a fault occurs, such as a short circuit or ground fault, the fault current will flow through the EGC back to the source. This high current flow will cause the overcurrent protective device to trip, interrupting the circuit and preventing further damage or injury. The size of the equipment grounding conductor is determined by the size of the circuit conductors. The National Electrical Code provides tables that specify the minimum size of the EGC based on the ampacity of the circuit conductors. It is important to use the correct size EGC to ensure that it can effectively carry the fault current. In addition to its role in fault current protection, the EGC also helps to reduce electrical noise and interference. By providing a low impedance path to ground, the EGC can help to filter out unwanted electrical signals that can disrupt the operation of sensitive electronic equipment. The equipment grounding conductor is an essential component of a safe and reliable electrical system. It provides protection against electrical shock and fire, and it helps to ensure the proper operation of electrical equipment. The NEC specifies the requirements for equipment grounding in Article 250. This article covers topics such as grounding electrode systems, equipment grounding conductors, and bonding. It is important to understand and comply with the requirements of Article 250 to ensure the safety of electrical installations. There are several different types of equipment grounding conductors, including firstly, wires. Wires are the most common type of EGC. They can be either bare or insulated, and they are typically made of copper or aluminum. Secondly, metallic conduits. Metallic conduits, such as steel or aluminum conduit, can also be used as EGC. When using metallic conduit as an EGC, it is important to ensure that all connections are tight and secure. Thirdly, metallic cable trays. Metallic cable trays can also be used as EGC. When using metallic cable trays as EGC, it is important to ensure that the cable tray is properly bonded to the grounding electrode system. Fourthly, other metallic enclosures. Other metallic enclosures, such as junction boxes and panel boards, can also be used as EGC. When using metallic enclosures as EGC, it is important to ensure that the enclosure is properly bonded to the grounding electrode system. Bonding is the process of connecting different metallic parts of an electrical system together to create a continuous electrical path. Bonding is important for safety because it helps to ensure that all metallic parts are at the same electrical potential. This reduces the risk of electrical shock if someone comes into contact with a metallic part that is energized. The NEC specifies the requirements for bonding in Article 250. This article covers topics such as bonding jumpers, bonding bushings, and grounding clamps. It is important to understand and comply with the requirements of Article 250 to ensure the safety of electrical installations. There are several different methods for bonding metallic parts together, including firstly, bonding jumpers. Bonding jumpers are short lengths of wire that are used to connect two metallic parts together. Bonding jumpers are typically made of copper or aluminum, and they are sized according to the ampacity of the circuit. Secondly, bonding bushings. Bonding bushings are used to connect metallic conduit to metallic enclosures. Bonding bushings have a sharp edge that bites into the metal of the conduit and the enclosure, creating a good electrical connection. Thirdly, grounding clamps. Grounding clamps are used to connect grounding conductors to metallic parts. Grounding clamps are typically made of copper or bronze, and they are designed to provide a secure and reliable connection. The purpose of bonding is to create a low impedance path for fault currents to flow back to the source. This low impedance path allows the overcurrent protection device to quickly trip and clear the fault, minimizing the risk of electrical shock or fire. Bonding is required in a variety of situations, including firstly at service entrances. Bonding is required at service entrances to connect the grounding electrode system to the neutral conductor and the equipment grounding conductors. Secondly, at separately derived systems. Bonding is required at separately derived systems such as generators and transformers to connect the grounding electrode system to the neutral conductor and the equipment grounding conductors. Thirdly, at metallic enclosures. Bonding is required at metallic enclosures such as panel boards and junction boxes to connect the enclosure to the equipment grounding conductor. Fourthly, at metallic conduits and cable trays. Bonding is required at metallic conduits and cable trays to connect the conduit or cable tray to the equipment grounding conductor. Bonding is an essential component of a safe and reliable electrical system. It provides protection against electrical shock and fire, and it helps to ensure the proper operation of electrical equipment. It is important to understand the requirements of the National Electrical Code and to follow them carefully when installing and maintaining electrical systems. The grounding electrode system is a critical component of an electrical system, providing a connection to the earth that helps to stabilize voltage and provide a path for fault current. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes, that are connected to the building's electrical system. The purpose of the grounding electrode system is to provide a low impedance path to ground for fault currents. This low impedance path allows the overcurrent protection devices to quickly trip and clear the fault, minimizing the risk of electrical shock or fire. The NEC specifies the requirements for grounding electrode systems in Article 250. This article covers topics such as grounding electrode types, grounding electrode installation, and grounding electrode conductors. It is important to understand and comply with the requirements of Article 250 to ensure the safety of electrical installations. There are several different types of grounding electrodes that can be used, including firstly, ground rods. Ground rods are the most common type of grounding electrode. They are typically made of copper or copper-clad steel, and they are driven into the ground to a depth of at least 8 feet. Secondly, ground plates. Ground plates are large, flat metal plates that are buried in the ground. Ground plates are typically made of copper or galvanized steel, and they are buried at a depth of at least 2.5 feet. Thirdly, underground metallic water pipes. Underground metallic water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The water pipe must be electrically continuous and must not have any insulated joints or sections. Fourthly, concrete encased electrodes. Concrete encased electrodes, also known as UV grounds, are grounding electrodes that are encased in concrete. Concrete encased electrodes are typically used in new construction, and they provide a very low impedance path to ground. The grounding electrode conductor is the conductor that connects the grounding electrode to the building's electrical system. The grounding electrode conductor must be sized according to the ampacity of the service conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service conductors. The grounding electrode system is an essential component of a safe and reliable electrical system. It provides protection against electrical shock and fire, and it helps to ensure the proper operation of electrical equipment. It is important to understand the requirements of the National Electrical Code and to follow them carefully when installing and maintaining electrical systems. When dealing with cable trays and conduits, the NEC provides specific guidance to ensure a safe and effective grounding and bonding system. Article 392 of the NEC covers cable trays, while Article 344 addresses conduits. These articles outline the requirements for construction, installation, and use of these wiring methods. Within these articles, specific sections address grounding and bonding requirements, ensuring that a continuous and reliable path to ground is maintained throughout the electrical system. For cable trays, proper bonding is crucial to minimize impedance and provide a path for fault currents to flow back to the source, facilitating the quick operation of overcurrent protective devices. This typically involves bonding the cable tray sections together using appropriate bonding jumpers and hardware. For conduits, grounding and bonding are equally important. When metallic conduits are used, they can serve as equipment grounding conductors if installed correctly with proper connections and fittings. Non-metallic conduits require a separate equipment grounding conductor to be installed within the conduit. In situations where conduits are run from a cable tray system, the NEC mandates that the conduit be bonded to the cable tray system even if the conduit already contains an equipment grounding conductor. This is to ensure that the grounding path is as robust and reliable as possible. The bonding connection must be made using approved methods such as bonding jumpers or grounding clamps, and the size of the bonding conductor must be adequate to carry the available fault current. The specific requirements for bonding conduits to cable trays can be found in the NEC. It is important to consult the latest edition of the NEC and to follow the specific requirements outlined in Articles 250, 344, and 392 to ensure compliance and safety. Failure to properly ground and bond cable trays and conduits can create a dangerous electrical hazard, increasing the risk of electrical shock, fire, and equipment damage. Therefore, it is essential for electrical professionals to have a thorough understanding of the NEC requirements and to follow them carefully when installing and maintaining these wiring methods. Always consult with a qualified electrical inspector to ensure that the installation meets all applicable codes and regulations.